Today we're very happy to have our own Shaowei talking to us about safety by shared synthesis. Looking forward to it.
Yeah, thanks, David. Hi, everyone. So today I'm going to be talking about the work that Topos has been doing with Atlas Computing on AI-assisted formal verification. And at the end of the talk, I will also share some of my own personal findings, my own personal lessons from doing this project with Atlas. So I think some of you might remember the CrowdStrike incident back in July. And what happened was that there was a Microsoft update, and there was a bug in the update, and it caused all the many Windows systems to crash, especially at hospitals and airports, and there were tons and tons of delays at the airports because of this. So I think that the safety of our socio-technical systems is something that we think about and we are concerned about, not just in the case of bugs like this, but also like with AI becoming more powerful. We are worried about AI systems getting out of control and then maybe hacking our socio-technical systems and doing things that we did not intend for these systems to do. So the question is, how do we want to fix our socio-technical systems? Do we fix them one bug at a time? Do we just wait for things to happen? Just kind of related to this issue of trying to fix our bugs, the White House recently had a memo in February this year saying that future software should be memory safe. They didn't say that it has to be using Rust as a programming language, but Rust is definitely one of the languages that many people are considering right now. And memory safety is something I think that plagues many of our existing software systems, and this shows that there's a push at the government level to try to solve these kinds of issues. Now, how can we harden our software systems? And one way is by proof, by using mathematical proof. So a really good example of this is the ComCert project. So ComCert was an attempt to write a C++ compiler that is verified, and so one of the very nice comments about this compiler was in 2011 was that this group of people did a bunch of tests on different C compilers, and they said that ComCert was the only compiler that we have tested for which CSmith, which is their platform for testing compilers, could not find wrong code errors. And this is not for lack of trying. We have devoted about 6 CPU years to the test. So they basically attacked the ComCert compiler with 6 CPU years worth of compute, and they could not find anything wrong with it. But writing formal specifications, implementations, and proofs for software like this is hard. For instance, for the ComCert project, you can see that in order to prove that the ComCert compiler is correct, they had to invent 9 different intermediate languages in order to do this, and it involves years and years of work and many different project groups. And the question is, how can we scale something like this? What Topos and Atlas is proposing is that we can scale formal verification with AI assistance. And here in the little GIF that you see here is an example of what AI, this is a GitHub Copilot. What AI is able to do these days, you could write a comment describing what you want the function to do, and GitHub Copilot now gives you something called ghost text or a suggestion of a program that could solve that problem. And the problem with this approach is that language models they tend to hallucinate, and they tend to have issues with reasoning. Although with O1, I hear that it's a lot better now. The question is, how can we ensure that the code that they produce is actually correct? Now, another strategy to scale formal verification is to create formal tools for allowing humans to collaborate and to make sense and to decide what our socio-technical systems should be doing. And if we want mathematical proof that our software systems are correct, we have to at least write down theorems. We have to at least write down specifications of what these systems should do, and who should decide these specifications. Do we want AI to decide these specifications, or could we collectively get together as a community, come down and put on a drawing board a list of properties that we want our systems to do, and then we have a way to engage each other in dialogue in deciding if those lists of specifications or properties are actually enough. And I want to argue, so this is something that Topos has been working on. We want to argue that for such a dialogue to happen, we need our tools to be conceptual, interoperable, and formal. So here, conceptual means that the tool should be understandable by users. So if your user doesn't know type theory or category theory, will they understand how to use your tool? And if they don't, then the tool is useless. By formal, we mean that the artifacts that we are creating with these tools, they should be checkable by a machine. And by interoperable, it means that we might have different domain experts, experts working in different domains, and there should be a way to translate between formal specifications in one domain to another, or at least to talk about translations or subsets of things like that. And interoperable to us also means version control. So as you dialogue with others and negotiate what kinds of properties you should have, there will be different versions of those specifications. So you have to think about how those versions are being accounted for in your formal tool. So I think broadly, these two strategies. One, which is using AI models to help us in scaling the finding of proofs, for instance. And number two, having formal tools for us to have the dialogue about this is the general gist of this report that we came up with, that in order to scale formal verification, we need better formal tools for dialogue, and we need better tools for constructing proofs and implementations.
But are these two strategies totally orthogonal, or are you going to try to synthesize them?
Yeah, that's a good question. So I think they, in principle, they are orthogonal, but they interact in very interesting ways. And I'm going to actually show you some of that right now. So this is, oh, Dana?
Could you go back 3 slides there?
Yeah.
You had that
3 slides.
diagram. One more.
Ah, yeah.
Okay, so those guys had to make all those decisions there. You can't claim that an AI is going to make the decisions that they made and putting that together.
Exactly.
I mean, that's years of experience in doing compiling.
Exactly. We are not claiming that AI should replace all that. We are, I think the word that we are using is assistance. So AI can assist with the mundane parts of this, but in planning and designing this, definitely we need humans in a loop. Yeah. Okay. So this is the systems. This is the summary diagram that we have in our report. The link to the report you can find at the bottom of the slide. So you can see that in very broadly, we have humans deciding what the intent of the social technical system should be, and then documentation of the behavior of the system in fulfilling that intent. And we think of all this as happening in natural language. On the other side, we have deployments. So in deployments, you have interfaces, and we have executable binaries. So we think of the interface as describing what the binaries are doing, and the executable as the thing that actually runs the program. And then in the middle, we have a framework for bridging the natural language on one side and the deployment on the other side. In this framework, we have specification logics for describing our intents, our specifications. It's a formal logic. And then we also have an implementation logic that usually describes the kinds of programs that you can write. And at the top level, again, you will see that we have either a specification or a theorem or the type of the implementation. And the bottom, you see that we have proofs of those specifications, and we have proofs that we have an implementation that satisfies the specification, or we have the implementation itself on the other side. And then finally, the implementation is compiled into an executable at the last part. Already in this diagram, you can see that there are many kinds of interactions that needs to be negotiated. One obvious one is how you would translate a human natural language intent into a formal specification. We could use some kinds of, maybe some AI models for doing the translation from natural language to formal spec. we also have aspects of translating so this part where we translate from natural language to specification is called auto-formalization. And then we also will have to translate the formal specifications back to natural language so that humans can check and understand if the formal spec does exactly what they want it to do. And I misspoke just now. Interagent here is thinking more in terms of the UX, of how you can design, implement all these different components into something that feels natural for the human. So for instance, what we do not want interagent to be doing is where the human has to copy and paste things into ChatGPT and back again. That would be a really bad UX design. But we are exploring different ways where somehow the AI assistant can feel more natural in the background. So that's one aspect that needs to be designed more carefully. And in here, you can see also other aspects where, for instance, you have suppose you have legacy code, legacy implementations. How could you design specs for that? You could perhaps get an AI model to help you in suggesting a possible spec for your code, so that implementation to spec. Or you could start with a specification, and you can ask how I can synthesize an implementation from that, and that would be spec to spec implementation. And yeah, there are a few other components, but I will kind of talk about that later on. Yeah, Kevin?
Cool. It's a pretty sick chart. Let's all just like take a breath with it for a second.
Yeah, please.
See whether there's anything more you would expect. I'm wondering about the far left side, about the distinction between intent and documentation. My left, sorry. The
Yeah.
natural language side.
Right.
So interagent is like the thing that you're worried a lot about, the UX the human is interacting with is to like mutually construct a spec.
Yes.
And like auto-formalization is maybe more of just is not so much of a agent you interact with, but just like a process that just churns out a bunch of good documentation from a spec or something.
Right. I think, yeah, that's right. Here we're separating the HCI aspects in interagent, and then auto-formalization, I think of it more as the algorithms that underneath the hood that's helping you do the translation. Dana?
Has anyone ever tried taking a paragraph of mathematical text and translating it into formal logic? Has anyone ever tried that?
Yeah, I think there are many people who have tried that. Terrence Tao writes a lot about that, and in fact, later I'll show a little demo of what you can do or what you cannot do at this point with language models.
That's a start.
Yeah, that's a start. Yeah, thanks. Evan?
So I'm wondering how what's going on in these different white boxes is
Yeah.
either the same or different. Like, is it that in each case we're asking the LLM to translate from one natural or formal language to another, or does each one involve special design?
Yeah, each of them involves special design. So for instance, at the end of today's talk, I will show you something that we're doing on auto-formalization. You definitely cannot just use LLM out of the box. You have to do a little bit of clever designing to get better results. From our experience, using the language model out of the box does get you somewhere, but usually not enough for you to have a system that humans can trust, a translation that humans can trust, or a spec that humans can trust. We need to build in design more structures to support the process so that we can increase the trust in the system.
And one last little thing. So every white box is like a big, huge open problem, pretty much.
Yes, yeah, that's right. So this tool chain, so Quinn mentioned in one of his announcements about this tool chain, this is a very massive research project that no one company should try to attempt to solve all these different white boxes at the same time. And so far, in Topos' work with Atlas, we are focusing just on this one box here, auto-formalization. Yeah. But we know of different research groups which are working on various other boxes, and we talk to them all the time. There are groups in Stanford doing this, in Harvard, in companies like Gawa, and we talk to them to find out their progress on these things. Okay. So yeah, definitely there's a lot more I can say about this diagram, and if you're interested, please go to the linked PDF file, and there'll be more details in there, and I sure would love to hear feedback. If you have any questions about the document, please come to me, and or you have questions, please check that with me. Okay, so as Dana asked, if you use the language model out of the box, what can we get so far? And here I'm going to show a little example of translating natural language to specs. Okay, here I'm going to ask ChatGPT to write a factorial function and prove that the factorial is always positive. So right out of the box, ChatGPT likes to explain everything. And then soon it writes a function in lean. Okay, it defines the factorial function, and then it goes on to try to prove that the factorial function is always positive. You could say that, well, the factorial function is very simple. There are probably lots of math text out there that was used to train ChatGPT, and this is not a hard problem for ChatGPT at all. And you're absolutely right. In many of our cases, the experiments that we're doing, if the thing that you're trying to code is more obscure, we do find that ChatGPT is really struggling to translate the natural language to specs.
That's all correct, though?
Yes, that's another good question. So it turns out that that's correct Lean 3 code. Lean 3 is from the last generation, and clearly GPT was trained on Lean 3. Lean 4 is the newest thing. There are many problems that people are talking about right now. Terrence Tao on Twitter yesterday just talked about how GPT-01, it does not seem to understand Lean 4 notation or generate Lean 4 notation. That's quite a bummer. But these people expect that these problems will go away once they are trained on newer data. Okay. Right. Here, I want to show you a quick demo of how GPT can convert code to specs. So you give it a legacy code, and then you give it a piece of legacy code. Here, the code is, I believe, for binary tree. No, for finding. I think this is for finding the maximum element of an array, and we are going to ask it to write down specifications in a verification language called Daphne. Okay. You have to give quite a bit of prompts to kind of guide it on what kinds of specs that it should not write. But after you give it the right prompting, it seems to do quite well. So it will tell you that, so here is the code for finding the maximum element of an array. And it turns out the preconditions that you need is that the array is not empty, and the post condition should be that the return element should be one of the elements in your array, and that it should be bigger than or equal to everything else in the array, right? And it actually gets it right, and if you take this code and you check it in Daphne, it actually runs correctly as well. Daphne is a quite well-known language, and we expect GPT to do quite well with Daphne. So this is an example of GPT writing specifications from code. Okay, and lastly, here's a little demo of a program called Lean Copilot. There is here they are starting with so Lean Copilot is an integration of GPT or any other chatbot that you care about into Lean, where it would help you in writing proofs for your mathematical theorems. Okay, so you can get the chatbot to suggest tactics that you can use for your proofs. You can get the chatbot to search for a full proof. So tactics is just suggesting one step of the proof. Searching for a proof would find you the entire proof. And then lastly, you could say, I have no idea how I should continue. Find me a lemma that I should apply to my theorem. And so you can ask GPT to select a premise for you. So this is still very initial work by the Lean Copilot team, and they did say that for instance, the proof search is not all quite that great. It needs a lot of help or assistance from the human to find the right proofs or to guide it in the right direction in improving. So, so this is kind of like the state of the art. Although these days, I think you might have heard that O1 is able to solve problems for Math Olympiad problems. In the same way, they convert the Math Olympiad problems into Lean, and then they try to get Lean to find a proof in Lean. Okay, so that's just kind of a teaser of the extent to which language models can get you for some of the white boxes that you saw at the diagram in the beginning. Okay, and so now I'm going to give a little bit more of a detailed commentary of what actually goes on in formal verification. So currently in formal verification, there are two large classes of verification languages or frameworks. The first are what we call auto-active frameworks, and the second are what we call expressive or interactive frameworks. In the auto-active framework, the word auto there suggests that the proof is being found automatically, somewhat automatically or mostly automatically. And these frameworks are based on like Hoare logic or separation logic, and the proofs are usually found by using SMT solvers. And examples of those frameworks are like Daphne, Pharmacy, and Verus. And we also have more expressive frameworks which are often built on dependent type theory, and they often in finding proofs you often need more interaction from the human, and some of the frameworks include Coq, Lean, and Agda. So I want to talk a little bit about how if you're given a specification, how you could try to synthesize code. So the problem of synthesizing code is something that many people are concerned about these days. You could get AI to write code for you, for instance, using GitHub Copilot. But anyone who's actually tried to use that, they will tell you that the code that is given to you is often correct in terms of the steps that it's trying to do, but it might get the syntax wrong. It might make some errors, very small errors, that introduces a bug that's very hard to fix. And sometimes you end up spending more time trying to fix the bugs in the AI-generated code than actually solving the problem on yourself, by yourself. So how do we get the accuracy of, how do we get code generation to be more accurate when using AI models? And so the first insight about how we should do this is that I personally believe that the way that we're doing code generation today is wrong. We are generating code token by token. If you go back to my GIF of Copilot, you see that it actually generates the lines of code one word at a time. And when you do that, it often means that there could be some syntactical errors that are introduced by this token by token generation. How do we then avoid those syntactical errors? And the answer is that you should think about code not as a collection of words, but you should think of code as having some larger hierarchical structure. So maybe at the top level, you're writing an if-then-else statement. Perhaps for each of the parts of your if-then-else statement, you're computing some kind of a Boolean, or you're taking some kind of action, or you're calling another function. So the code breaks down hierarchically. And what we should do is we should first think about this code as a hierarchical structure. And secondly, we should think about different parts of the code as possibly being missing or having a hole if we are not yet done with our program. So if you think of the program state as, if we think of the state of synthesis as a program with holes, then what we should be doing is taking actions to transform this program with holes into another program with holes. And those actions that we take, they're called tactics. And an example of tactic-driven program synthesis is in this paper by Adam Chipatler and his team at MIT using a software called Fiat. And this was a 2015 paper. So in this paper, Adam and his team, they were trying to think about how you could synthesize code. For instance, here's an example of him trying to synthesize a piece of code that inserts a key value pair into a list. And you want the list to contain the key value pair if the key is new, but if the key is already in the list, there's no need to insert this key value pair. And so he starts off with a very generic description of the task, and through a series of refinements. So here, a refinement means that you think of this top thing as a list of possible list outputs that you can have to this insert function. But as you refine, the set of outputs will become smaller and smaller until you only have one possible output, and then this the program that generated that one possible output would then be the result of your synthesis. And the way that he drives this construction by refinement is through tactics. Also on the right side, you see a list of the tactics that generated the refinements that you see on the left. Okay. Whether we can do this with AI models today is still something that that people are working on. I think that this is not the general way of synthesizing programs today, but it will definitely it seems to be able to give us the accuracy that we want in terms of synthesis. The second thing is the second strategy for program synthesis is to use machines for getting rid to use machines in getting rid of ambiguity. So, for instance, if I'll give an example. I'll start with an example, and then I'll describe the general philosophy of it. So, suppose you have equality, the equality operator, and you're trying to implement that in your lean proof assistant. So, you want to show that two natural numbers are equal, or you want to show that two booleans are equal. Now, you could have a different constructor for each of these equalities, okay? Which means that the next time you need to prove something about booleans, you have to perhaps design tactics that allow you to do reflexivity or symmetry or transitivity. And then you kind of have to do that for booleans. And then if you try to do equality for natural numbers, you have to reconstruct all these different tactics for the natural numbers. So one way you can do this, you can avoid repeating all these tactics, is to create a type class for all equality operators. And in this type class, for your equality operator to be a part of this type class, you have to provide proofs of the standard stuff like reflexivity, symmetry, and transitivity. So at the end of the day, what you end up with is an overloaded equality operator. Your user does not need to remember if he's using the operator for booleans or operator for natural numbers. The machine will fill in the blanks. It will actually automatically guess which equality you're you're referring to by the context of where the operator is being used. So this is what I mean by letting the machine fill in the blanks. And by being very explicit in designing your theorems and lemmas and your definitions this way, you can get very, very far with existing tools, even without AI. So this is the strategy that was used to prove the four-color map theorem, the four-color theorem and the odd-order theorem. And the description of how they tackled these big proofs is described in the book Mathematical Components. So now that we have language models that can do a lot more than
Sorry, Shaowei. I think the slides are not showing exactly what you wanted to show.
Oh, are you seeing inside too right now, Valeria?
I'm seeing slides, but for instance, I can't read the definition of equality because it's much smaller than the stuff about.
Oh, don't worry about it. I think, yeah.
That's okay for you?
Yeah, that's okay for me. Yeah. Okay. So all this was done without AI language models. I argue that if we have these generic tactics and generic type classes that understand large classes of similar structures, it will be easier for AI models to apply tactics across different problems from different domains. So if we really want to scale the use of AI in proving theorems or in synthesizing programs, we really have to learn how to work with type classes for synthesis, or type classes of similar structures in programming or in proofs. And lastly, we talked about having collective tools having formal tools for collective dialogue, for dialogue and sense making. And a really good example of this is what's recently happening with the liquid tensor project in math, the proof of the FPR PFR conjecture, or the formalization of infinity cosmos by Emily Real. And what they're doing is that they are using a proof assistant as well as a software called Blueprint. And Blueprint allows you to visualize all the different lemmas and theorems that need to be formalized. And the color would then tell you the state of formalization for those things. And it turns out that with these tools that allow us humans to get together to write down theorems or write down specs and then to collaborate on proving different lemmas, you can get progress way faster than what was previously possible when everyone was just using WordPress and trying to coordinate things through WordPress. So having the formal tool, the formal proofs, and being mitigated with coordinated with a software like Blueprint gives you profit. And then the last thing I would say about the toolchain is that you should not think of formal verification as a linear process. It doesn't start with specification, and then once you're done with that, you lock it up, you kind of write it in stone, and then you start working on the programs and proofs, and then finally you export it out into a program and executable. Most of the time, specifications, they change. People will find out, oh, I think I formalized it incorrectly. I need to change one aspect of the specification. And the moment you change the specification, everything downstream is going to change. The proofs have to change. The programs have to change. So it is really important that we allow for the evolution of your code, your specs, your proofs over time. And so to do that, we really need to look at tools like proof repair and proof equivalence, checking if two implementations have the same behavior. So this is something that we talk about in the toolchain, the report, but I'm not going to go more into details about this. Any questions at this point? Okay. And yeah, so the summary of this is that we have two strategies for scaling formal verification. One is to use AI models, and the second is to create tools for collective sense making. And that I also discussed a little bit about synthesis, how we should be doing it tactic by tactic and not token by token, and that we should let machines fill in the blanks as much as possible with type classes. So now I will share a little bit of the lessons that I have from doing this project. But if we don't get through this, I think it's fine. I think the main things I wanted to cover. So I think one of the big things that was very interesting to me was that refinement as a strategy is very, very general. It covers different kinds of problems, both in programming and in proofs, and as well as perhaps other kinds of systems that we care about. And I gave a lightning talk about this previously, but I kind of want to repeat it again. If you're given, so there's a paper called Functors are Type Refinement Systems. You can look up the PDF of this. In there, they say that if you're given an arbitrary function between two categories, D and T, you can think of it as a type refinement system. So if you, for instance, if you have an object S in D, and that is mapped by the functor to an object A in T, then we say that S refines T. Oh, sorry, S refines A. Okay, and the symbol for that is up here. You can see the S refines A. You write it as S with a square bracket, include bracket A. That's how you write that S refines A. And a typing judgment will be a triple S, F, and T, such that S and T define the domain and codomain at F. In other words, the U mapped to U of S is A and U of T is B, and F is a function from A to F is a morphism from A to B in your category T. Okay, so the way that we describe this is over here we have S. We have SFT is a typing judgment is if S maps to A and T maps to B. And then lastly, you say that alpha is the derivation of the typing judgment, alpha is a morphism in D between S and T such that alpha is mapped to F. Okay, so we're not doing anything fancy here. We are just adding maybe new kinds of definitions to existing things that we know about functors. And there will be now an additional notation with the inequality sign here if U and V, they map to the same object, and that this beta morphism here maps to identity. Okay, so we write it as an inequality. You can think of it as a, yeah. So the reason we're writing this as triples, SF and T, is because we want to show that its relationship to, to Hoare logic, but I'll talk about that in a while. But first, why are we thinking here? We have this category D of derivations. I want to talk a little bit about what derivations are. All right. So from type theory or logic, we know that derivations, they often involve some kind of context at the top, and then there is often a logical rule. Say this is elimination, and then here you have the result of that judgment. So you can think of this rule here as a morphism in D, and then you can think of the things at the top at the bottom. These contexts, they are objects in your category D. So we have, so your derivations are in your category D up there. They could be coming from some kind of a logic or type theory, and they could be of derivations of this form. You can, yeah. And then if that's your category of derivations, then what is your category of terms? Usually in the category of terms, we look at, we remove proof information from your category of derivations, and you just stick to the object. So for instance, in your category of derivations, you could have this subtype here of even numbers, which is that, so you have a natural number n together with a proof that you could write n as 2 times some natural number k. But in the terms, in the category of terms, you forget that information, and all you have is just the type of natural numbers. Okay, so yeah. So the refinement, the type refinement system that I showed you previously, they generalize some of the logics that we see at work in formal verification. So the simplest example would be Hoare logic. So in Hoare logic, you take your category T of terms to be states, to be objects in your state space, and morphisms, to be states, and then morphisms are transformations between states. And then in your category D of derivations, you want to your objects are going to be predicates over those states. So you have a state and a predicate that the states satisfy, and your morphisms are going to be a state transformer to get together with a proof that the state phi, that if you start off with a state phi and you apply the transformation C, you're going to get a state satisfying C. So this category of derivations, they contain predicates about your states as well as proofs about how those predicates are being preserved. And then lastly, your functor du will be your forgetful functor. And in Hoare logic, you often write down your statements as triples. So P here would be preconditions on your state. S here will be some kind of transformation, state transformation, and Q here will be a postcondition on your state. And you can then reason like this: if you have a state Q with some predicate, if you have a predicate Q on the state that is somehow intermediate between P and R, and then you have transformations between them, then you can compose them to get this new triple. Okay. Separation logic is a generalization of Hoare logic. Here, the states are often described as consisting of a store and a heap. So the store is supposed to correspond to your variables in a programming language like C, and then your heap is supposed to correspond to your memory locations where you store values of those variables. And so separation logic was designed to help people reason about what their programs are doing without worrying about memory safety, without worrying that somehow your program is doing something really weird with your memory where you could actually writing a value to one memory state actually overwrites another memory location and then which then causes your whole program to fail. So you want to eliminate concerns like that. And that's why separation logic was designed. And in separation logic, you also have triples of the form that you saw in Hall logic. And you can see that this is why in this paper here, they wanted to define typing judgments as triples to show you the parallel with what's already happening with Hall logic and separation logic. Okay. Now, some of you have been working with Rust a lot. And the reason I'm talking about Rust right now is because Rust plays a very special role in formal verification, right? Previously here with separation logic, we talked about being able to argue about what your function is doing without worrying about what's happening with memory. Rust is, by design, memory safe. A lot of people think of Rust as a low-level programming language, but really Rust is a formal verification framework. The reason we say that is because in your Rust code, you add annotations like the ampersand sign or the mutable or mute here to talk about who owns different variables in your code, and then how you could perhaps borrow out. You could have another function borrow a variable that you own and then do something with it and then return it to the original owner. And by doing this, this is how Rust gives you memory safety. Most of these annotations that you've added here, you really can think of them as preconditions and postconditions that you're adding to your code. And these pre and post conditions are being checked at compile time. At runtime, they're removed. They are never checked at runtime. And so this is, in this sense, this is very similar to a programming language like Daphne, where pre and post conditions are checked at compile time, and then you export your Daphne code out into, say, C or Java, all right? And then at runtime, all these pre and post conditions are not checked out; they're removed.
But this is a very restricted logic for pre and post conditions, right? Like I can change this guy while it's running, right?
Yeah, exactly.
I can emulate all core logic.
No. Right. Rust will not be able to emulate all Hall logic. There is a programming language there's a framework called Verus that tries to do that. So it's trying to add Hall logic on top of Rust.
How's that spelled?
Verus is Verus. Verus. Yeah. But it's quite a new project, and it's quite interesting to see where they go from here. Okay. So. So one of the lessons I've learned from this toolchain project is that Rust is playing a very important role in formal verification today, and it's likely going to change the field a lot. If you think of a lot of the problems that people are trying to solve in the past about verifying code as trying to resolve issues of memory safety and pointer safety and things like that, Rust takes a lot of those issues away so that people can actually focus on what the code is doing. And as a result, in our work, in Topos' work with Atlas, we are focusing a lot on Rust and building formal verification on top of Rust. Okay, so we kind of seen refinement happen at different levels, right? So we talked about refinement very generally. We talked about Hall logic and separation logic, and we saw refinement happening within Rust in trying to reason about ownership. Now, the synthesis, program synthesis method that I talked about in the first half of the talk, this work by Adam Chipatler's team, Fiat, it's also a special case of the refinement, type refinement system that I just described to you earlier. Here, what you have to do is you have to take this diagram and you flip it upside down. Okay, if you flip it upside down, then this is the result of your judgment derivation, and this will be the assumptions that you make before you can make this judgment. So if you flip everything upside down, then you can see that you have a sequence of derivations that gives you the program that you want, and that each of these can be written as a triple. These triples are then passed into a solver to be checked, and that's exactly how Fiat does it. Underneath the hood, there's an SMT solver that partially resolves many of the proof goals, and then it's not complete. So there are certain proof goals that Fiat is not able to resolve, and they hand that back to the human to be resolved. Okay, so more generally, this is a discussion I had with David and Evan yesterday. We want to go beyond the kinds of refinement that we see in programming, and that more generally here at Topos we've been looking at composing systems. We can think of, for instance, if we have this wiring diagram here where we have a diagram which I'm going to call a goal, G1, that takes in certain inputs and gives out certain outputs. We could then refine this goal into this other diagram here that has two sub-goals, G1, G2, and G3, and there could be holes in your system in that we don't actually know what to fill in for those two different boxes in there, but everything else outside of G2 and G3 are wired up. We can think of that as a kind of refinement. And so as we take our goals and we refine them and decompose them into smaller sub goals, we also have to keep track of the codes that we are generating through this process. So, for instance, if we have a code C2 and a code C3 that fills in that satisfies these goals, we have to compose them together using the way specified by the wiring diagram above to give us a code C1 that fulfills our goal G1. And if these wires here, they come with, they're actually typed wires, or if they are dependently typed wires, then you might have to give a proof that the wiring that I did over here is in fact going to give you the right type for the outputs of this diagram here. And so in addition to composing the codes that we get from this decomposition, we may have to keep track of the proofs that are being generated, the proofs that are required to ensure that the types of all the inputs and outputs are respected. Yeah, Quinn?
What makes a wire dependent? Like, is there like a pictorial difference between
dependent
and simple wires?
I don't know if there's a good way to draw like dependent wires, but if you, for instance, if you have, say, type A here, and then for this input here, and then you could have a type B that depends on A. Mm-hmm. Those would be the kinds of dependent functions that you could have in dependent type theory, but it's not. I don't know if there's a nice way to draw this. Yeah.
Is this the same phenomenon that Sophie and Carrie were drawing over the summer with an extra like light blue squiggle in the box? That kind of dependency?
This is perfectly good as long as you don't have a symmetric, as long as you can.
Oh.
I mean, this is pretty good to allow things to be dependent. Yeah.
Oh, I like that. Yeah.
Yeah, I guess asymmetry does
Yeah.
kind of capture dependency in a way.
Mm.
I like that.
Yeah. So yeah, dependent types, there are many systems that we work with that do not have dependent inputs, and we want to ask about synthesis in those scenarios as well. And so if we are able to put all of this synthesis, program synthesis of a more general kind into this refinement framework, we can then perhaps ask how we can use AI models to generate tactics that can help us to refine and help us to synthesize solutions to this problem. Okay, I think this is the last thing I'll say, which is that synthesis is not just restricted to programs and proofs. So for instance, in the work that we are doing with Atlas right now on auto-formalization, which is translating natural language intent to formal specs, we are taking the intent and we are thinking of the spec as a spec with holes, and that we apply tactics to break down the spec with holes into other specs with holes. And so there's a kind of refinement process in trying to translate this natural language text into a formal spec that you see at the end of the chain over there. Okay, so synthesis is also very useful for deriving specs. Okay, and then I think that's it for my talk, and I will open up the time for questions, and if people want to see demos, I can also do that. Thanks. Dana.
In the big diagram, you had some gray rectangles, and I guess that meant you thought those were already known how to do those.
Yeah, that's right. So the gray, that's a good question. So the gray things here include like the proof checker between the proof and, okay, that actually checks, yeah, the proof against the specification. And then we have the extractor that could take a proof and extract an implementation from that, removing all the proof information, and the compiler that compiles it to binary. So those are not part of our, those are not research goals or research projects. Yeah, David?
How well do you understand the blueprint software stuff? Like I remember something.
I've not used it myself.
Okay. I remember something like you have an informal statement in white, and then a formal statement in blue, and then a
Yes.
proven statement in green, or one of the color schemes.
Right.
But how? Yeah. I guess I'm wondering. Clearly, green.
Yeah.
Like once you've proven it, you've proven it.
Yeah.
But how do you know? How do they tell in that blueprint software whether the formal spec is of the English language informal statement?
So I think all this is handwritten. There is no checks in Blueprint. I think once in the GitHub repo, once you have a proof of your theorem that's checked by Lean, someone manually goes over to Blueprint and colors it green. That's as far as I understand. I could be wrong. And then as for the human natural language description of the theorem, which is written in LaTeX, it's manually written. It's not written by an AI.
And nothing checks it. Yeah.
Yeah, they don't actually check that the natural language version of the theorem actually matches the formal theorem.
How would you check it?
Oh, I have no idea. I mean, I just wondered, like, how they are they competing? You have
yeah.
competing, like, what if 10 different people formalized it, and
I don't think
I
you.
wondered if you know how. Yeah.
No, I think it's still very manual at this stage, and it would be nice to see if we can automate that. Yes.
Shaowei,
Yeah, Valeria, you have a question, and then Quinn, I'll get to you.
I would like to see some of the auto-formalization stuff that you were, because I saw previously some stuff, but I was also going to mention that the blueprint stuff, it's actually the fact that it turns green is automatic.
Oh, okay.
So once the piece of the theorem has been accepted by the by Lean, then it's automatic.
I
But
see.
you're right.
So what Valeria is saying, I'll just repeat it for the room. If the theorem is proved in Lean, then the conversion from blue to green is automatic in Blueprint.
But from white to blue is automatic.
I don't.
Not yet.
Yeah.
I was going to suggest, Shaowei, because I had someone called Pietro Monciconi give a tutorial on Blueprint in the Bonn trimester. We could invite him to give another tutorial for us, but it is recorded in the Bonn videos.
Ah, okay, very cool. Yeah, Valeria's telling us that. What's his name again?
Pietro Monciconi.
Pietro Monciconi. Yeah, is
For you.
yeah. Thanks. And then we may contact him. But thanks for that. Yeah, so he's giving a blueprint in Bonn about Blueprint.
And he also produced a template so that you can, like Emily mentioned, that it was with him that she managed to get her Infinity Cosmoi sorted out, because he has this template for making the blueprint
I see.
follow up with the interaction with Lean.
Wow, very cool. Okay, I see. Yeah, so some setup is needed to make sure Lean talks to Blueprint. Quinn, you have a question?
It's more of a remark with followed by what do you think.
Yeah.
But I noticed we're a little bit on time. But all I just wanted to point out was that, like, you can in principle map a specification to a type if you assume certain things about your target type system. So like the extraction can almost like close the gap. The reason you don't do that is because you don't assume those things about the type system. You assume that the type system is weaker in your target language than in your specification.
That's right. That's right.
Language.
Yeah.
And a sort of related thing is that there's this like heuristic where like, you know, a proof and a program aren't that different, except a proof is where you don't care about which proof you find, and a program you care about which program you find. And that might sort of lead to issues if we like do tactical proofs, which like don't give us a fine-grained way to control like which proof we're finding. We're just finding a proof. And then if we do some extraction, I mean this has been studied in like the Coq to OCaml extraction, the Coq to Haskell extraction, but it could be the extraction could be problematic for that reason, where you're going to find like if your specification language isn't fine-grained enough to make it so that like there is one non-trivial solution to every spec. Unless you have the specification language that's fine, that expressive, you might be a little bit messed up.
Yeah, that's a good point. Maybe I will respond to that privately. About this, and I think. Two more? No, I don't mind. Now that it's 12, I just want to make sure that maybe okay. David and Chris. Okay.
I was just wondering. I think I missed the part about interframework. What is that?
Oh, I didn't talk about that. So interframework is translating between different frameworks or theories. You could have translate, like say, between Coq and Lean. Like right now, we have lots and lots of for instance, program synthesis tools in Coq, and then we would like to translate it over to Lean.
But it's not about like levels of abstraction or that sort of thing.
Levels of extraction? No, not really. Yeah, not
like
quite.
From what people, human users versus like in a nuclear power plant or something. I don't know what we're specifying here exactly.
Yeah.
Maybe just code, but is it eventually going to be towards like industrial checking or just code checking?
Okay, I would say that it could be general to the kinds of levels of abstraction that you're talking about, but in our toolchain we're not thinking about that. And right now, interframework collects together a lot of concerns that people have right now about like how, for instance, we have lots of Coq libraries but not that many in Lean unless you're in math, and that we have lots of code in C but not a lot in Rust, and how do you do that translation? And translation is actually not easy at all. Like there's a big DARPA program for translating C to Rust, and some of the examples they gave is like if you just do like word for word translation, you often don't get safe Rust code, for instance, things like that.
Okay, I think we better actually stop.
Yeah.
And I'll charge Shaowei.
Okay. Yeah. Thanks.